Hello, so in this video we're going to have a look at rates of reaction, and this is the first video just looking at calculating the rate of reaction using our formula, our graphs, our reasons why a reaction may increase, and the two required practicals. We'll do another video on reversible reactions and equilibrium. So we're going to start off by looking at how to calculate the rate of a reaction. And we can do that by measuring the quantity of the reactant used or the quantity of the product produced over time. Now, remembering our reactants are the chemicals we react together to cause a reaction, and our products are the chemicals that we form from a reaction. We measure that per unit time. So we have two formulas. They're pretty much the same thing. So we have our rate of reaction is either the quantity of reactant used divided by time, or the quantity of product formed divided by time. Both will give a rate. And importantly, the quantity of the product or reactant will either be in grams or in centimeters cubed. You need to make sure it's in grams or centimeters cubed. Now, very occasionally, they may give it to you in moles. And our time will always be in seconds. So we need to make sure we've always got it in grams or centimeters cubed for our quantity, and our time is in seconds. So let's have a look at a worked example. So this one here, we've got 96 grams of magnesium sulfate is formed in 45 seconds. What is the rate, the mean rate of reaction? We're looking at the reaction over the whole period of time. Now, to do this, I recommend that you follow the FIFA way of calculating or doing calculations. So for that, we have our first F stands for formula. So we're going to write down our formula. And they may give it to you in the exam or they may not, but it's always good to start off by writing out the formula. So that formula is our rate of reaction equals our quantity of product formed, because we've got our magnesium sulfate being formed, divided by the time. And next part from the FIFA acronym is the I. So for that I, we're going to insert our values. So our values are 96 grams for our quantity of product formed, divided by 45 seconds. Now, by doing it like this, we know we're not going to make any mistakes. We now need to fine tune. That's our next F for FIFA. Fine tune means, do we need to make any readjustments or any rearranging of the equation? So have we got to convert any units or rearrange the formula? Well, I'm looking at this and I'm saying, right, my quantity of product formed is in grams and my time is in seconds. So for that, I'm happy. My quantity is in grams and my time is in seconds. There's no fine tuning needed. I'm now going to use my calculator to get an answer. So I press 96 divided by 45 and I get my answer, so that final A. And we get 2.13 grams per second. My units here are grams per second. It's important we know what this is. Are they going to be grams per second or centimeters cubed per second? Let's have a look at another one. This time we've got 150 centimeters cubed of hydrogen gas being formed over 35 seconds. What is the mean rate of reaction? Now, don't be alarmed that it's now gone to centimeters cubed. This cubed here, we don't need to do anything with it. We're not going to cube any numbers. It's just telling us what the unit is. This is our unit here. So again, we're going to go with our FIFA. So our formula, insert values, fine tune, and our answer. So our formula is rate of reaction is the quantity of product formed divided by time. That's exactly the same step each time. We're now going to insert our values. So we're going to use the question for this. So I've got 150 centimeters cubed, and I've got 35 seconds. I need to make sure I put them in the right place, which is why I've written out my formula here. For that, I get my rate of reaction equals 150 centimeters cubed divided by 35 seconds. Now my fine tune, do I need to convert any units or rearrange the formula? You might be tempted to say, oh, do I have to rearrange that into grams? We don't need to turn that into grams. We can use centimeters cubed. That is absolutely fine as well. So I put those values, they're all the same. I put those values into my calculator and I get my answer of 4.29 centimeters cubed per second. Now I've rounded my answer to 2 decimal places. Question hasn't told me to, but that's a good way to go. If it tells you to go to 3, then go to 3, but generally go with 2 decimal places. And my units this time are centimeters cubed per second. I've got that from my equation. I've got centimeters cubed divided by seconds. It's the same thing here, centimeters cubed divided by seconds. Got a final one to look at. We've got 3.54 kilograms of carbon was used up in 350 seconds. What is the mean rate of reaction? I'm going to start this exactly the same way with my formula first. So my formula is rate of reaction equals the quantity of reactant used divided by time. I'm now going to insert my values. I'm doing this directly from the question. So my rate of reaction equals 3.54 kilograms, that's how much of my reactant was used, my carbon, divided by 350 seconds. I now need to fine tune it. So do I need to convert any units or rearrange the formula? Let's have a quick look, shall we? So I've got 3.54 kilograms divided by 350 seconds. Well, I need to have it in grams, so I need to convert this 3.54 kilograms into grams. My time, the 350 seconds, is absolutely fine. My units are seconds there. So I need to convert that 3.54 kilograms into grams. To do that, I'm going to multiply it by 1,000. If we get stuck with this, take it back to 1 unit. So I've got 1 kilogram, and how many grams will that be? Well, I know in science we like using multiples of 1,000. So if I've got 1 kilogram, that's going to be 1,000 grams. So I can think the same for 1 kilometer is 1,000 meters. That kilo means 1,000. So I'm going to multiply it by 1,000. I can put those back into my formula now. So I've got 3,540 divided by 350 seconds. My answer, I then get 10.11, and my units here are now grams per second. I'll be really careful to make sure I convert those units. Now we don't always, or we very rarely, they will give you the values straight off. They will often give you the values to read from a graph. And from the graph we need to calculate our values and our time. Now the reason we use graphs is because the gradient can tell us something. On here we've got our gradient and we can see that it's going up. As it goes up, this means the reaction is occurring. We start off with quite a steep gradient because at this point here there's a lot of reactants that can react together to form the product, so a reaction is very fast. Towards the end of the reaction it begins to slow down. At this point here it's very, very slow because there's not many reactants reacting together, so the reaction has slowed down. When my line is flat at the end, it is now finished. There's no more reaction happening, so at this point I know my reaction has finished. If I have a steep gradient, so we'll draw one on here, so if I have a steep gradient, I've got a steep gradient, it means my reaction is happening faster. Notice that I still stop at the same volume of gas being produced because the reaction has still stopped. I cannot make any more gas than this, I've just made it quicker. If I have a slower rate of reaction, it's going to go at a shallower gradient, but still get to the 25 centimeters cubed of gas, showing that because we can make no more, but this shows we've got a slower rate of reaction. We've now got a worked example here, and this is going to ask us, or it asks us to calculate the mean rate of reaction between 10 and 50 seconds. So I'm looking at the rate of reaction that is happening between 10 seconds and 50 seconds. For that I'm going to need to draw values on my graph. I want to find out how much I had at 10 seconds and how much I had at 50 seconds and how much was made over that time to work out my rate. I'm going to do the same thing though. I'm going to use my FIFA acronym, so my F or my formula. My rate of reaction is the quantity of products made divided by time. That hasn't changed, I'm still going with FIFA. I, for my insert values, well this time actually I need to use my graph for this value. So I'm going to start off by finding or doing what I've got with the graph. So I've got the times 10 seconds and 50 seconds. So I'm going to draw a line from 10 seconds up to the line of my graph, so this thick line that's going up, showing my rate of reaction. I'm drawing that line up to find where they intersect. So I know that's at 10 seconds. I'm now going to draw across the line from my the graph to my y-axis. So going across, I draw that line and I find where it meets the y-axis and write my number down there. Now I've put that as being 6 centimeters cubed. I'm now going to do the same for 50, so I'm going to draw a line from 50 up to where it intercepts the graph and label that at 50 seconds. I'm now going to go across from my graph, where my 50-second line intercepts the graph, to my y-axis. I'm going to go along there, and I find that that is 24 centimeters cubed. My next step is to find the difference between them for all of these values. So my quantity made is 24 centimeters cubed minus 6. I'm finding out the difference between these two values. So I do my larger number, take away my smaller number to get 18 centimeters cubed. I'm now going to find out my time. So again, same process, I'm going to do 50 seconds minus 10 seconds to give me 40 seconds. That was my time. I can now put those values into my formula. So I get 18 centimeters cubed divided by 40 seconds. Do I need to do any fine tune or any rearrangements? Nope, I don't. My units are all correct. I've got centimeters cubed and I've got seconds. So I'm now going to put that number into my calculator. I'll do 18 divided by 40 and I will get my answer as 0.45. My units are centimeters cubed per second. Apologies, that cube sign should be, superscript should be up in the air, but I didn't do it when I made it. Very sorry about that. Now there are times, so if you're doing the higher paper or triple, you will need to find the rate of reaction at a particular time, and this gets very, very confusing. So it will happen in all three sciences. You will get a question on a graph asking you to find the rate of reaction or the rate of something at a particular time. So to do this, we need to draw a tangent to the line. Now, this gets a little bit tricky, but it is often worth a good number of marks in our exams when we can do it. So I'm now going to calculate the rate of reaction at 30 seconds. So this isn't looking at how much was made at 30 seconds, I'm finding the rate of reaction at 30 seconds. So it would change throughout the whole reaction. It will start off faster and get slower. Now for that, I need to first write out my formula again. So my rate of reaction is the quantity of product made divided by the time. I'm now going to insert my values. Now for that, I need to use my graph again. I'm going to draw a line from 30 seconds up to the graph to find out where it intercepts. And I've got that point there. So this is where I want to draw my tangent. Now tangent is a line that just touches the curve. So I need to be quite careful when I'm drawing this. So I'm going to draw it on, and I've drawn mine about here. I know it's not completely touching, but we can see what we're going for. So once we draw it on our graphs in the exams, the examiner can see what you're doing and you will get marks for it that way. I'm now going to find my time. So I'm going to pick a value. I'm going to draw a triangle around it. So I've drawn a triangle to find out the gradient of this line. It's just the gradient of a straight line at this point. So my x values, so my x-axis values, I'm going from 0 up to 60 seconds. So I've got my time is 60 seconds. My y value, so my volume, my y-axis, I'm going to go from this 5 down here up to the one up here, which is 31. So I've gone from 5 to 31, which is 26 centimeters cubed. I can now put those values into my calculator or into my formula. So I've got my rate is 26 centimeters cubed divided by 60 seconds. I don't need to do any fine tuning because all of my units are correct. So I can put those numbers into the calculator and I get my answer of 0.43 centimeters cubed per second. And we see that is slightly different to the one we got before, between calculating between 10 and 50 seconds. Now, in the exam, you will get a bit of leeway with how you calculate this. There will be a range for the answers, but the examiners will be looking to check that you have drawn a tangent and calculated the gradient of that tangent correctly. So our next bit is now looking at explanations of our reactions, and we use something called collision theory. Now, collision theory helps us to explain why the rate of a reaction will increase or decrease. So we need to know our theories and then be able to apply them as well for our explanations. So collision theory simply states, for a reaction to occur, the particles of the reactants need to collide with enough energy. They have to come into contact to have a reaction, and they have to come into contact with enough energy to either break or make those new bonds. And that kinetic energy, so the particles are moving, they've got kinetic energy, needed for the reaction to occur is called the activation energy. The energy we need to activate a reaction. If we think back to C7 and we looked at those temperature changes, those graphs, you would have had that little bump on a graph that was the activation energy, the energy we need to start the reaction. Now we've got 5 ways that will increase the rate of reaction, and we need to know what they are and how they increase the rate of reaction in terms of particles and collisions. Now these answers are all fairly similar to each other because we're talking about the numbers of particles and how they collide, or how they move and how they collide. Now our 5 ways we've got are surface area, temperature, concentration, pressure, which is for gases, and the use of a catalyst, which is a bit of a different one. So first off, we're going to look at surface area. So if we increase the surface area, so the outside area of the reactants, that increases the rate of reaction because there are more particles available to collide, so there are more frequent collisions that meet the activation energy per unit time. So we're talking about the number of particles, and then we get more frequent collisions that meet the activation energy. And this per unit time just means per second, so it's how quickly it is happening. Now surface area, we can increase that in a number of ways. We can chop something into small pieces, or we can crush it into a fine powder. All of that makes the surface area larger. The next one we'll look at is temperature. So our temperature increase, so an increase in temperature increases the rate of reaction because the particles have more kinetic energy, so they're moving faster. That means we get more frequent collisions as those particles move around and collide that meet the activation energy, again, per unit time. So our last bit here, we're just saying there's more frequent collisions that meet the activation energy per unit time. Very, very similar answer. Our part that's changed is that actually our particles are moving faster or have more kinetic energy. So we get more frequent collisions that meet the activation energy per unit time. Next one is concentration. So our concentration will often be for an acid. We'll have increased it from 1 mole to 2 moles or 0.5 to 1 moles, but we've increased the concentration. The concentration of something is the number of particles we've got per unit volume. So the number of those acid particles that are in the beaker. The more concentrated it is, the more particles we've got in there. And with this, we can say that an increase in concentration increases the rate of reaction because there are more particles available to collide, so there are more frequent collisions that meet the activation energy per unit time. Again, very, very similar answer to what's going on. We've got this first part has changed slightly. We've now just got more particles available to collide, so there are more frequent collisions that meet the activation energy per unit time. Our next one is pressure. Now this is only for gases. Now with pressure, it's very similar to concentration. If we increase the pressure, we are increasing the concentration of those gas particles within that volume. So we're making it appear there's more gas particles per unit volume. So very, very similar to concentration. So an increase in pressure increases the rate of reaction because there are more particles available to collide, so there are more frequent collisions that meet the activation energy per unit time. Now all 4 of those answers have the same ending. We get more frequent collisions that meet the activation energy per unit time. Only thing we need to change is what is going on, so why we're getting more frequent collisions. So for our surface area, it is the number of particles available. For temperature, it's the particles are moving faster, and for concentration and pressure, again, it's the number of particles available to collide. Our final one is a catalyst. So with a catalyst, this is slightly different. Now, a catalyst is a substance that increases the rate of a reaction without being used up. So it will make the reaction happen faster. Now, it can be another chemical, or it can be different enzymes that we find in things. For example, they could be in a piece of liver, in a potato, in a carrot. They will all work as catalysts. Now, a catalyst works by lowering the activation energy. We've got a lower activation energy, more of those particles that collide will reach that activation energy. So we can say we get more successful collisions per unit time. Alternatively, we can say that a catalyst provides an alternative route for the reaction to take place. If you go on to study A-level chemistry, we look more about those alternative routes. For the moment, we're happy enough just to know that it does provide an alternative route. Our final part of this video, we will look at the two required practicals we need to know about. Now, both of them look at how concentration affects the rate of reaction. Now, we've got one with magnesium and hydrochloric acid, and one with sodium thiosulfate and hydrochloric acid. Now, this one with magnesium and hydrochloric acid, they may try and trick you and put in another one and give it a different metal and a different acid, but the process is exactly the same. The sodium thiosulfate and hydrochloric acid, they will keep the same. So for our magnesium and hydrochloric acid, we've put the method on here. We've got lots of things. This is a very, very clear method. It's the kind of thing you might be expected to know for how to answer a question asking you about the method for it. This is the kind of thing you would want to write. So it's worth pausing the video and going through it and learning it. You can learn it off by heart, that is absolutely fine. You may also want to draw a diagram. So this is the diagram that you would want to draw. Now you may remember trying to set up this piece of apparatus with the measuring cylinder and the trough of water, and no, actually it's pretty hard to do. So alternatively, you may want to use a gas syringe to collect the gas as well. Now they may also ask you about the variables within this practical. So we have our independent, dependent and control. Our independent variable is the one that we change. Our dependent variable is the one that we measure, and our control is what we keep the same. So on here, our control, we could look, would be the volume of acid, or the strips of the size of the magnesium. We'd also want to do it on the same day, at the same temperature, using the same equipment, timing for the same time, to keep everything a fair test and make sure it is reliable. Now our independent variable, the thing that we are changing, is the concentration of the acid. So we're changing the concentration of acid. We're using 1 mole per decimeter cubed of acid and 1.5 moles per decimeter cubed. That 1 mole means that we've got 1 mole of acid in every decimeter cube. Decimeter cube is a litre. The 1.5 means we've got 1.5 moles per decimeter cubed or per litre. So we've got a bit more in there. Our dependent variable is the time taken to produce the gas. So we can then work out our rate of reaction from that. So please pause the video and note this down so that you know how to do this practical. Our final one is sodium thiosulfate and hydrochloric acid. Again, we've got the method here. We're changing the concentration. This one requires you to calculate or to make up your own concentrations of sodium thiosulfate by mixing a certain amount of it, sodium thiosulfate, with a different concentration of water. And we can change the volumes of sodium thiosulfate and water to give us a different concentration of it. We react them together and we swirl a flask. We start a stop clock and we look down and we see that it starts to form a precipitate. That is a solid that is insoluble, so it's not dissolving in the water. And we time how long it takes for the cross to disappear. we record that time, we can then compare them and see which reaction is faster. Again, we may want to draw a diagram. This is the kind of diagram we'll be seeing. It's the kind of diagram they will use in the exams as well, and say this is the diagram you've got, talk about this practical. If you see this diagram, you know what we're talking about. Now, our independent variable is the concentration of our sodium thiosulfate. It's the one thing that we're changing each time. Our dependent variable is the time taken for the cross to disappear. I've given you the equation here. You're not expected to know this. You may be asked to balance it, but you're not expected to know it. If we look very carefully, we've also got the state symbols. So this AQ means aqueous. It's something dissolved in water. This L is our liquid. This SO2 is our gas. This is sulfur dioxide. It smells a bit like rotten eggs. And this S here is sulfur. The little s in brackets stands for solid. And this solid is what makes the solution turn cloudy. That's why we can no longer see it. The faster this sulfur, or our solid, is produced, the faster the rate of reaction and the quicker the X appears to disappear. So again, please pause this video to note down the method for this, because you may have to write about this in your exams. Thank you very much for watching. I hope this has been useful. There are some questions on the sheet attached, so please try and complete those as well to the best of your ability. Thank you very much. Have a great day. Bye bye.